Um, Thank you so much, Lucy, and your team for giving us this opportunity to actually talk about this exciting topic and our work with Fraunhofer together. Um, Unfortunately, my co-worker, colleague, Theodora couldn't attend this presentation because she's sick, so she will be fortunately replaced by Nicola today. And Nicola will help us uh, during the presentation to answer any of your questions as well. So yeah, so to begin with, um, yeah, before we talk about quantum enhanced multi-agent reinforcement learning, I mean, I'll like to take a step back and tell you, or at least talk about motivation to actually go in the direction of quantum enhanced machine learning algorithms in the first place. Why do we want to explore quantum enhanced solutions in the first place? So if we talk about it, for example, there are two major reasons that I like can talk about for our reasons to move from classical AI to quantum AI. One of them is, of course, the domain that that we are operating in or that we are working in. Planes are not anymore just some parts flying together. They're a lot more than that. They have a lot of sensors, they have a lot of data that needs to be processed, that needs to be used to do some kind of prediction. Um, Machine learning techniques or data driven techniques are used even in the designing phases in these kind of industry. So yeah, it's one of those industries which is heavily dependent on data. The second reason is, of course, as we all know, AI is of course it's a hot topic. LLMs are even hotter topic right now, but we also see that the community is also trying to find different alternative because they know that at one point of time they will reach their limits in terms of how much of calculation they will require or how much of computation resources that they will require. And one such alternative for us, for example, is indeed to explore quantum enhanced solutions. Given the potential that they have shown for certain type of use cases, where they've shown that they can do better generalization in certain problems, they can do better generative. They have better generative abilities in some use cases and can enhance basically the generative AI models in a good way by using some kind of quantum enhancement over there. Then yeah, they've in some of the research work they've also seen to capture complexities with fewer parameters, fewer trainable parameters. So basically reducing the model complexity, yet capturing the complexity in the data. And of course, then comes with reinforcement learning, where they've also shown like you don't need a lot of iteration through simulators. Sometimes you can train complex policies with lesser amount of data. But this is all like potential advantages that we have seen in many of the previous works. Of course, it's dependent a lot on the use case that we're talking about or the problem that we are talking about, and in many cases the data that we're talking about. So of course, the use case space for us is huge because we apply these kind of solutions in aerospace domain, from designing to in the end to even when let's say for some kind of autonomous operation. Of course, the solution space is also very huge. So meaning we need to explore the benefits that quantum enhancement can have for generative AI models or reinforcement learning models and etc. So of course we can't do everything alone. We can't explore everything alone. So we collaborate with the ecosystem. We work together with the industries, universities, and one such collaboration effort that was this challenge, Quantum Mobility Quest. This was launched this year in collaboration with BMW and of course supported by AWS and Quantum Insider. And in this, therefore, specifically because we wanted to explore different solutions in quantum machine learning domain, so we specifically out of the problem that we gave to the participants to solve, we have one specifically focused on quantum enhanced multi-agent, quantum enhanced generative AI. And this problem statement was basically named as quantum enhanced autonomy. And what was the use case in a nutshell? Of course, we wanted to have the participant give us some solution that will help us in generation of some kind of critical test scenario images for our autonomous cars or autonomous planes, let's say, in the future. And why is that necessary? I mean, of course, data generation or acquisition both is really expensive. If you talk about planes, for example, if you want to capture images of runway from when the plane is trying to land, it's a lot expensive than just basically, of course, maybe a lot expensive than in comparison to some use cases in automotive field, but yeah, it's pretty difficult to do that if you want to actually capture the real data. So the idea was that we give this as a challenge to the participants. They will be given as an input image some kind of daytime images of runway or like the traffic scenario, and they are supposed to convert this image or using some style transfer or generative AI methods into nighttime images of runway or and the traffic for respectively for aerospace and automotive. And we already are running through this challenge already for some time. We already have 3 finalists for phase 2. So there's one team from University of Tokyo, there's another team from Kundela, and then there's another team, Quanet, which have already been finalized to fine-tune their quantum enhanced generative AI solution for this specific problem statement. So of course, with this in mind, this was not the only collaboration activity that we did, of course. So with this in mind, we also did some other collaborations, and one of such collaboration was with Fraunhofer, where we tried to explore quantum enhanced multi-agent reinforcement learning and its potential advantage while enhancing it with quantum properties with these solutions. The business application or business use case for that was like, let's say we have, of course, Airbus has a lot of flying assets. And what we want to do is basically put some kind of a direct communication link. So for example, laser or something similar like a directed link on these assets. And what we want in the end is that they are all connected to ground stations. So for example, to provide internet services on plane or something like that. But of course, the problem or the challenge is that we'll always have some kind of limited amount of simultaneous links possible. So that's one challenge. And the second challenge would be that the range of these kind of links would also be limited. So what can we do? Of course, we can do is, so the planes can decide if it's easier for them to just connect directly to the ground station. They just connect to the ground station. Else, if they cannot, they try to connect to another plane which is in the air in such a way that they basically in the end have a multi-hop connection to the ground station. Of course, it looks like a easy solution, but it isn't that easy if you look at from the machine learning point of view, because this the environment or the scenario that we're talking about is very dynamic. Planes are moving at a particular speed in different directions. So yeah, the AI needs to actually think about what should be the best candidate to connect with within its range. And this plane needs to do with the information that is provided to it only locally. So it does not see all the entities that are flying around, but it only can see some planes which are around it in a particular range. And based on that, it needs to make a particular decision on real time, independently and decentralized way. So in nutshell, the problem use case that we had from machine learning point of view is, okay, we want to predict better topology for communication and for a very robust and stable connection to ground stations. And the challenge, of course, as I've just talked, it's a highly complex problem and it's a very dynamic environment. So thus we thought maybe a quantum enhanced solution would be a better one, because we have seen in previous works as well that it can capture complexities better with fewer parameters, and of course this was one of the many reasons to move to quantum enhancement. With this, I'd like to hand over to Nicola, who will actually tell you more about how we tried to solve this problem using quantum enhancement linear reinforcement learning.
Thank you. All right, so let's talk about the setting here. So we have different agents connected by a binary variable. And the whole state, it's represented as a vector of binaries and continuous variable. In the case of continuous, we are talking about like the range from like a ground station. And when an agent is moving to the station, then the reward it's higher, right? So you want to be connected to the station. Then when it is moving like far from the station, then you get like a lower reward because you want the agent to connect to a neighbor agent that will have like a more stable connection. So you have like your entire state through binary and continuous variable. And what we have been looking before is about like previous publication on how to speed like the training up, right? So we saw that on the quantum machine learning side, you can you can enhance like the training view with less data. On the quantum reinforcement, instead, the hope there is to obtain like a better speed up in terms of iteration, so obtain like a good policy with less iteration, right? And the fact is that you have still like devices with a reduced number of qubits and affected by noise, right? So those are like the current challenges that we are facing. So the algorithm should be good enough to work on the NISQ devices and provide a sort of advantage over classical machine learning. So the overall training procedure is the following, right? So we have like central critic, which is shared among the agents, and it's just one central, right? And this is hybrid quantum neural network. And then the critic actually establish like an overview of the whole state into each individual agent, so that each agent, when is learning like an individual policy, it's not rewarding itself in an individual base, but it's rewarding the whole system, right? So in the end, you want to learn like a good decentralized policy that it's rewarding the whole communication. And what you do after the training is that you definitely deploy like just a classical machine learning system, so the classical machine learning network on the agent itself, and you don't need anymore the central critic, right? So you just use it for training, and then you just deploy, and then the agent works in the environment with the learned policy. The loss is taking into account all the different elements and then updating back the different policies and the central critic. To be a bit more precise, in this case, we use like a variational quantum circuits based on high order encoding for the feature map. This is, and a strongly entangled layer. So this is a sequence of C naught with rotational Y gates. And in this case, we have like, for example, for 4 qubits BQC, then we have 8 parameter on the variational quantum circuits, because the feature map is taking into account the input, and we are repeating also the feature map for each layer, right? So you have like a sequential encoding basically. And this is replaced into one layer or L layers of the classical network, right? So we first compress the system through the first layer operation, and then we pass through the variational quantum circuits. Now, and so this is like this setting. It's one of the most common in the literature. Probably it's not the best one or not the worst one, but it's one that we tested so far, and it was working okay. This is like the overall results. So you have like a variational quantum circuits described in 3 different categories. So the red one, the green one, and the blue ones. The variational quantum circuits can have like a normalized input through like just a norm L2 norm normalization on the input, or arctangent for each neuron. So you are just normalizing the input into B0 and 1s. And we are comparing against a classical neural networks, right? With 1 layer, 2 layers, or 3 layers, and we see that there is a bit of advantage over like the time step in learning like the policy. In the end, you obtain like a similar reward as the classical one with less iteration. For this specific setting, we are just dealing with 4 aircrafts and 1 base station. In case we are moving for 5 aircrafts and 2 base station, we see like a similar trend. So we still have like a better reward within less and few iteration. And yes, so for the comparison of instead the rand, so the random solution will be grounded at 85, right? So that will be like the lower bound of any policy. And yes, so to conclude about the study and to give you like an outlook is the fact that so you can actually heuristically think that hybrid quantum classical neural networks can provide an advantage over poor classical networks. You need to find like a good setting on where to compare them on a fair basis, right? And in this case, we are trying to gain some insight into the architectural components of the variational quantum circuits. So what kind of encoding to use, what kind of layers to use, right? And definitely you try to investigate the scalability of this approach, right? So if we are talking about a very large state that you need on the classical side, you're not able to reach a good policy anymore. That's where we are looking to get like the next advantage of real quantum computing. Thanks.